Welcome to Mastering Solutions. This problem, I'll be honest, is a pretty difficult problem, but once you understand the process of how to work through it, I actually think it's kind of a fun question. Let's make a list of everything that they give us in the problem first. So we're told that L is equal to, let's see, they said 25 millimeters. So 25 times 10 to the negative 3 meters for the distance from the diffraction grating out to the viewing screen. And then D, distance and the slit spacing, we have the width over slits or lines, and that is equal to 1 millimeter, 1 times 10 to the negative 3 for millimeters over 800 lines or slits. I'll leave it like this. We're also given the wavelength, of course. Lambda is 600 nanometers, and that's times 10 to the negative 9 meters. And we're also told that this is a first order, so M is going to be equal to 1. What they're talking about when they say resolution is to tell the resolution like on a TV screen, right? The higher the resolution, the more fine detail you can tell the difference. So what they're saying here is that the detector can barely distinguish between two bright lines that are 30 microns apart. So what they're trying to get you to understand here is that this 30 micron limit is the limit for this detector. Anything past that, it's like, nope, yeah, I can't tell the difference here. So when we find the difference in the wavelengths, that'll tell us how much of a difference in a wavelength this detector can resolve or see the resolution of. Just like a TV, the higher the resolution, the sharper the image. And so what we're going to do is we're going to use two equations, and we have to work forwards and then work backwards. And you'll see what I mean by that here in just a second. So we're going to use the equation y equals L times the tangent of theta. And we'll also be using theta is equal to the inverse sine of m times lambda over d. Now, the book gives it sine theta equals m lambda over d. I just moved it over with the inverse sine. This is very similar to the past couple problems that we've done. And in the past, we would do it in 2 steps. So we would start and find the angle here first and then plug it into this equation. For expanding our understanding, what I'm going to do here is I'm just going to make one big mega equation by plugging this value for theta into here. So that will be y is equal to L times the tangent of the inverse sine of m times lambda over d. So this is the whole equation that we're going to do. First, let's find what the y is for the 600 nanometers. So y is equal to L, which we said was 25 times 10 to the negative 3 meters. And then we'll take the tangent, and then inverse sine of m, which we said is 1, times lambda, 600 nanometers, over d, and we said that is 1 times 10 to the negative 3 meters over 800 slits or lines. Okay, so this is our whole equation, and let's plug that into the calculator to find the value for this. So we have 25 times 10 to the negative 3 times the tangent, inverse sine, and then we have m times lambda, and we said as 600 times 10 to the negative 9, divided by d, which is 1 times 10 to the negative 3, divided by 800 slits. Okay, that's a doozy. The answer is in meters, and we're going to go 1, 2, 3, so 13.68, so 13.68 millimeters, or times 10 to the negative 3. So that is the distance from the central max out to the first order bright fringe for this wavelength of 600 nanometers. They tell us that the distance from this out to the second line is 30 microns apart. And so what we'll do is we'll take 13.68 times 10 to the negative 3 meters, and then we're going to add 30 microns, so 30 times 10 to the negative 6 meters. So we have 13.68 times 10 to the negative 3 plus 30 times 10 to the negative 6. So that distance is 13.71 millimeters. So 13.71 millimeters. So what we just found, let's give us some more room. We just found that the first bright line, if we were to say this is the first central bright fringe, right? 13.68 millimeters, we'd have this line here. And then 30 microns away, the 13.71, we have the second line right there. This one right here, of course, is 600 nanometers for the lambda, but we don't know what this lambda is for this one. That's what we're trying to solve. So now we're going to take the exact same equation that we just found, and we have to rearrange it to solve for lambda. So let's rewrite the equation. So we have y is equal to L times the tangent times the inverse sine m lambda over d. So we want to solve it for lambda. So first let's divide both sides by L and then take the inverse tangent. So we have inverse tangent of y over L is equal to the inverse sine of m lambda over d. Now we can take the sine of both sides of the equation. So we have sine of inverse tangent of y over L is equal to m times lambda over d. And now we can multiply both sides by d and divide by m. So that will cancel, and that leaves us finally with lambda is equal to d over m times the sine times inverse tangent of y over L. So now let's plug all of the information in here and figure out what the wavelength for that second line is. Let's come up here so we have some more space. So lambda is equal to d, which we said was, and that's over 1 for the m, so I'm just going to leave this as d just for simplicity. So 1 times 10 to the negative 3 meters over 800 lines or slits. I'll put it in, divided by 1. And then sine inverse tangent of y, which we said is 13.71. We need that in meters, so 13.71 times 10 to the negative 3 meters. All of that is over, let's see, we said L, and in this case, our L is 25 times 10 to the negative 3 meters. So we have 1 times 10 to the negative 3 divided by 800, that's over 1. And we'll take the sine inverse tangent of 13.71 times 10 to the negative 3. That is divided by 25 times 10 to the negative 3 as well. So our answer is 1, 2, 3, 4, 5, 6, 7, 8, 9. So lambda is 601 nanometers. We started with one line at 600 nanometers, and we have the second wavelength as 601 nanometers. So the difference between those is 1 nanometer. So that is the resolution that this machine is able to detect down to changes in difference of wavelength of 1 nanometer, or its resolution.